How you doing? I'm Mr. Rose, and today we're going to introduce DC circuits. So to start, we're going to cover electric circuits. Electric circuits cover a lot of things in your everyday life, from your iPod to your iPad, your Samsung device, the phones that blow up. All of those things can be considered electric circuits, and most of them, as I just mentioned, happen to be DC electric circuits. Now, there are two types of circuits. There are AC circuits and DC circuits. AC standing for alternating current, anything that gets plugged into a wall. DC meaning a direct current, usually powered by batteries. In our course, we're going to focus mainly on our direct current circuits. There may even be some times where there is an AC current or an AC circuit that we assume is a DC current for the simplicity of our calculations. Now, we know by definition of a circuit is anything that has a power source and a closed conductive path connecting that power source. To make it a little more interesting, let's say I want to connect my power source to some wires and I want to move charge through a resistor. To do that, I want to connect each end of the resistor to one of two things. In the past, we talked about capacitors. Well, I can charge up a capacitor once it's fully charged. And after I charge up my capacitor, I can take my battery out, my power source, hook that up, and the capacitor will run charge through my resistor. But there's a problem with that. There's a small issue. The capacitor, when it's losing charge, doesn't have a steady state. In other words, its potential is not constant. And we want to have that constant potential. So even though this will work, it's not ideal. Second thing, or our second option, is producing that steady state with something called a charge pump. A charge pump is a fancy word for a battery. So the charge pump basically is going to do work on our charge carriers to move them from a low potential to a high potential and to get that current moving around the circuit. So we know charges flow in a circuit. What we've examined thus far is charges flowing because of an internal electric field. Even though we know electric fields can't run or can't exist on the inside of a conductor, we also know that there is a small electric field inside of the circuit in that wire that produces that charge flow. Well, we're not going to examine it that way right now. Now we're going to examine charge flow in terms of the energy required to move those charge carriers through my circuit. So here we have our EMF device, that script EE. That script EE stands for an EMF or a voltage. An older term is an electromotive force. Like I said, it is really just the script EE that's written all the time. And this is a device that does work on charge, namely our battery. Now here I have everything drawn in a very simple single loop circuit. I have a battery, and you might notice these arrows. I drew an electric field inside my battery. The top plate and the bottom of my battery, the positive and the negative. And we know an electric field goes from positive to negative. So there's a small electric field that exists inside that battery. Then we're using conventional current. Here's my current loop. And I've defined my current going to the right at the top, current going to the left at the bottom, which is my convention out of the positive into the negative. And I've defined the direction of my EMF, or my electromotive force, going from the negative side of the battery to the positive side of the battery. So what do we notice about this? We notice that for the circuit, we'll say that the circuit flows from high potential all the way to low potential. That kind of makes some sense. You'll also notice that inside of the battery, the charge carriers go from a low potential to a high potential, meaning they're moving against the direction of the electric field. So in order for that to happen, we need to do work on those small charges. So we're moving the opposite direction of the battery. To do work, we need a small amount of time. So by definition, we are moving charge carriers over a small amount of time. So by definition, this EMF, or my voltage, is a change in work divided by a change in time, which, as we can see, is a joule per cool, or a volt. Excuse me. There are two different types of batteries. We have an ideal battery, which I have drawn here. An ideal battery is typically what we use in lower level physics. An ideal battery tells me that the EMF lacks internal resistance. Namely, if I give a voltage, that voltage across my battery is also my EMF. So there's no difference. If I say the voltage is 12 volts, the EMF is 12 volts, that means the potential produced by these, around this terminal, if I have an A and a B, must be 12 volts. Now, a real battery does have some internal resistance. A real battery, I would say the potential is my EMF minus that internal resistance, minus IR. And we'll talk a little bit about that later. But essentially, that would mean that my total voltage would not be my actual output voltage. So, in order to calculate things around a single loop circuit, now there are different types of circuits. There are single loops and multi-loop circuits. Calculate a single loop circuit, we're going to need one of two methods. We're going to either use a conservation of energy method or a concept of potential. So recall our simple equation, power equals I squared times R. We also know power equals I times V. This is just a simple derivation. Well, since power is I squared R, if I want to know the energy, if I take that power, multiply it by some small amount of time, that gives us the energy. Well, in the same amount of time, I can move a charge. dq equals I dt. I'm moving charge carriers every second, that dt. The work from my battery, my very small amount of change of work, is my potential times my charge, dq, or it's equal to my potential times I times dt. Now, applying conservation of energy here, I can see that my voltage times my current times a very small amount of time is equal to the power I squared R times that same amount of time. Simple math, I can cross out an I can cancel an I squared, dt, and I'm left with Ohm's law of E equals I times R, or the voltage equals I times R in an ideal situation. This yields us to one of our methods, this potential method. Now, the potential method is also known as Kirchhoff's loop rule. So what is Kirchhoff's loop rule? In order to calculate the current through a single loop's wire, this potential method means if I start at any point in my circuit, so I come over here and I start at that point in my circuit. If I start here, I'm going to traverse my circuit in that direction. I'm doing that because I know the EMF is going in that direction. So I'm going to add my current arrow over there. I know there's current moving through this resistor over there. And what this says, if I start at any point in the circuit and I traverse around that total circuit, adding all of the potentials that I encounter, when I end, if I started here and, started there and ended there, or I would prefer to start and end here, my change in potential has to be zero. In other words, I'm going to get back to the same place I started with. If I compare that to gravity, a gravity example, if I'm on this mountain here, and I traverse around the mountain, I start at one elevation and I'm traveling around the mountain on this red dotted line, and I get back to the start. I may have gotten higher, I may have gotten lower, but at the end, the sum of my change in elevation is zero. So at the end, the sum of all this has to be zero. In other words, I need to utilize all of that potential. Kirchhoff's loop law says, the algebraic sum of a change in the potential encountered in a complete traverse, in a complete loop of that circle, all must add up to be zero. Now, in addition to this potential rule, there's also a resistance rule. Now, the resistance rule is quite simple. The resistance rule is saying, it's very similar to this, but now, as I move through a circuit in the direction of current flow, and again, in conventional current, I move through the direction of this current flow, so I'm moving around this circuit like so. As I move around, every resistor I encounter, I'm going to add that potential. That's what we have here in Kirchhoff's law. What that means is, this resistor right here, I'm going to add that potential, or that is minus I times R. So, very simple. In this simple circuit, if I started here, I would have plus E, because that is my plus E, that's my EMF rule. Plus the EMF minus I times R1 minus I times R2 equals 0. An ideal battery, it's very simple. My ideal battery is just an EMF, as we see here. As I move through a circuit, an ideal battery, negative to positive, the change in potential is positive because I'm doing work on there, and then I'm basically utilizing all of that energy, right? We're doing this with conservation of energy. Through an ideal battery, it would be very similar. Through a real battery with an internal resistance, very similar, except That real battery has a negative and a positive, and then has this little internal resistance. This dotted line represents the battery that I have drawn. So I would have my E plus E minus I times little r. I'm calling it little r because that's the internal resistance. Now, if you imagine this placed in this circuit, I would have plus E minus I times R for my real battery, traversing the circuit, minus I times R1 minus I times R2 equals 0. That's all we have on one of Kirchhoff's law. That's his loop law. We'll get a little bit deeper next time, and I have no fun puns for you, so I'll just see you next time. Thanks for watching.